We have here with us Mònica Aragüés. She's also from CITCEA-UPC, and she will talk about optimal power flow algorithm for meshed grids with HVDC.
Good morning. Thank you, Andreas, for this introduction. Yes, the topic is written and it is said, so I will not repeat it. The content of my presentation is structured as follows. First, we will give a brief overview on the context. Then we will see how can we operate these HVDC multi-terminal grids in an optimal way in terms of losses. Then we will move to an OPF, an optimal power flow, but for the whole HVDC-HVAC system. And finally, I will introduce a security approach to this hybrid AC-DC operation. What we have to keep in mind is that nowadays power systems have to face, on the one hand, an increase in demand, and on the other hand, a higher penetration of renewables. And this is not always accompanied by an appropriate expansion or adequation of the transmission systems. Mainly, we have three drivers for the transmission system expansion. And we can say they are HVDC technologies, FACTS, and HVAC. I will not say anything about HVAC today because I think it's out of scope compared to the other two topics. HVDC, we know it enables bulk power transmission. It also allows us to interconnect asynchronous power systems, and it allows the transmission over long distances. Flexible AC transmission systems increase, let's say, the controllability of the grid, and they also allow to optimize the existing infrastructures of the grid. I think that you have seen a similar slide to this one, so at least the pyramid should ring the bell. This is the investment criteria from the European perspective. The transmission system expansion should be based on the security of supply, on the competitiveness of the electrical market, and on a sustainable development. So, why not basing this transmission system expansion on HVDC? We have seen that there are some initiatives of building a supergrid. Especially the north of Europe is working towards it because we know that practically more than 70% of the offshore wind power is concentrated in the North Sea. I skipped this slide. This is a project. Sorry, this is a project. This is real. We have many HVDC point-to-point existing links. You can see them in red line. And we have some planned or considered HVDC links, and you can see them in dashed blue line. So, in case we are going to construct a multi-terminal DC grid, it's clear that first we are starting with HVDC point-to-point connections, and maybe in the future we will build multi-terminal grids and meshed grids. Although this attractiveness, we can identify many challenges on HVDC transmission. Mainly, the configurations, I already mentioned them. Are we going to build point-to-point or multi-terminal? Protection and grounding issues. Also, the kind of converters, design and topologies. We have also to take into account the right integration of HVDC with the already existing HVAC power system. There are also regulatory issues in terms of governance, ownership, grid codes. Also, with which levels of DC voltage shall we operate this multi-terminal DC grid? If we are going to use communications, as Agustin mentioned, we need also to ensure that we can operate the system when we have a loss of communications. And finally, we have or we should operate these DC grids in an efficient and secure way. And we have to keep in mind that we need control strategies to ensure the power flows inside these HVDC grids. These are the two topics where I'm focusing today. It is clear now that the future European transmission system could look, as you see in this slide, as constituted by HVDC grids and HVAC grids. They enable the integration of renewables. On the left part of this slide, you can see offshore wind power plants. Now I'm going to present an optimal power flow for ensuring minimum transmission losses in these HVDC transmission systems. So let's focus first on this DC side and forget the AC side. In normal operation, what we expect is that the offshore wind power plants inject all the power into the DC grid, and the grid side converters will be in charge of the DC bus voltage control. It's a classical solution to do so with the known droop control, which is mainly based on building a current reference for the grid side converters based on the voltage difference between the actual DC voltage and a certain reference or offset. The advantage of this scheme is that does not require any communication system to work, but it does not ensure minimum losses in the HVDC grid. If we have a communication system available, we could operate the grid based on solving periodically an algorithm that will give the voltage references for the grid side converters based on knowing the power being injected from the wind farms and knowing also the electrical characteristics of the DC grid, so being able to know its conductance matrix. If we compare both methodologies, we can see that the optimum voltages algorithm allows a reduction of losses significant when the power being injected from the wind farms is quite low. So there is no difference in losses when both algorithms operate when the power being injected is maximum, but as we reduce this power, the reduction of losses increases. So what we can conclude comparing these two algorithms is that the DC voltage control on multi-terminal networks is not as straight ahead as in a point-to-point connection. Droop control is a robust solution, but it does not ensure optimal losses for any power being injected from the wind farms. And let's say we can optimize these power flows. We can maximize the power injection from the HVDC grids. Why not taking advantages of both control schemes? We could have a low-level droop control, which would regulate the DC current based on this DC voltage difference, and on a higher level, we could have this optimal power flow algorithm that ensures minimum losses. So this would enable to perform secondary and tertiary strategies on the DC grid, taking advantages of both. This hybrid proposal, or this merged proposal, would look like this. We would have, we would know the power being injected from the wind farms, and this would be sent as, based on solving an OPF, we would send some references to the droop control, but not directly, because we could have some spikes on power and current. So what we propose is to limit the increase or decrease of the reference sent. Let's now move to the operation of the whole AC-DC system. The goals we are fixing now is try to design an optimization tool that ensures the optimal operation of the whole hybrid HVDC-HVAC grid. This could be seen in the perspective of minimizing transmission losses, minimizing the deviation from a preset voltage profile, minimizing generating costs or other objective functions. The problem is characterized as a nonlinear constraint optimization. It obviously involves AC and DC power flows. And if you want to know some characteristics of the software used for For solving it, you can see them at the bottom left or bottom right of the slide. The inputs for this, let's say, algorithm would be the conductance matrices of the DC and AC grids, the active and reactive power generation and demand, and the converter loss parameters, because in this case we are also taking into account not only the Joule losses inside the cables of the DC grid, but also the converter losses. The output would be the different DC voltages and currents on the DC grid, the voltages and in magnitude and angle of the AC grid, and the active and reactive powers on the different nodes. I would be a little bit fast on these slides. Yes, I think the chairman appreciates. Basically, what we did is benchmark the results we obtained with this tool with another tool, and we applied them to this system, which is a 3DC 5AC system, and where we know the demand of the different nodes. You can see the power flows for the DC system and for the AC system so as to ensure minimum losses. If we analyze the result on the voltages, we can see that the algorithm tries to keep the voltages as high as possible to ensure this maximum power transmission. So, there's an expression in Spanish which says, no es oro todo lo que reluce. I think in English it would be something like, it's not gold all that glitters, or something like this. And this also happens with HVDC. Hybrid HVDC HVAC grids could be a solution for transmission system expansion, but, for example, HVDC enables a higher penetration of renewables, but this introduces uncertainty on power systems operation because of the inherent variability on these sources. On the other hand, the security of power systems can be compromised, and also this can imply dangers for the accomplishment of the N-1 security criterion. All this will add complexity to the study of the reliability of these kind of systems, and a question that rises is up to which level of security shall we operate them. So this is why I introduced the last point. Oops. And it's the security constraint optimal power flow approach. Here we are taking into account a high wind penetration scenario, taking into account the uncertainty and fluctuation of offshore wind power. Also, the spinning reserves of the system are being taken into account, and the goal here is to maximize social welfare, or in other words, to minimize the generating cost of the different generating power plants. The questions that we would like to answer are, if the AC grid is operated N-1, how should we operate the DC grid? And how much wind power needs to be curtailed? The contingencies considered are the outage of all the elements, all the possible elements of the grids, outages of AC lines and cables, generating units, DC lines or cables, and even VSCs. Transmission system operators have mainly two strategies to deal or to face these contingencies, and they are the preventive and the corrective actions. We will focus on the corrective actions, which are the post-fault measures, and an example of this would be like changing the set points of the VSCs. This system you can see on this slide is based on CITCEA, so as Agustí said, it's a quite useful organization for performing or for obtaining data for studies. We have two big wind power plants, two big aggregated loads, and in the middle, as interface, we have a 4-terminal HVDC system and a 4-terminal HVAC grid. On these two graphs, what you can see is the different wind power available depending on the hour of the day and depending on the day of the month. And on the right, you can see the active power demand in one of the loads. I will not develop the methodology of this study because I don't have time, but you can see that there is quite difference in terms of cost and in terms of wind power curtailed when you compare the different levels of operation of the grid. For example, when we compare the operation between the DC grid N-0 and N-1, assuming that the AC grid is operated N-1, we can see a significant increase on the cost and on the wind power curtailed. Finally, I would like to conclude saying that HVDC is an enabling technology for transmission systems expansion, and it facilitates the renewables integration, but many challenges still remain. And at least this is very interesting in terms of for research people, because there's a lot of stuff to be done yet. And finally, transmission systems expansion with HVDC needs to be designed, operated, and controlled, taking into consideration the HVAC. We have two power systems, but connected between each other, so they need to be taken into account together. And that's all. Thank you for your attention.
Thank you very much, Monica. So we have time for question. There's one there.
In your opinion, what is the most favorite optimal power flow calculating algorithm that in order to control smart grids optimally?
Which is the best algorithm?
Yeah. There are like examples like linear programming, you can say, because it is not manual labor. Everything is controlled by computers. So what is the best calculating algorithm for nowadays?
It's a very general question, but I don't know. I mean, obviously you need a fast algorithm with low computation time, and you need the system to be able to operate continuously. So you need an algorithm that always converges, and in case you need communications, you need to ensure that the power system can keep on working in case they are lost. So I don't know which algorithm or which optimal power flow shall I tell you as answer, but at least it should have these requirements.
Okay, thank you. One question: the methodology you developed, does it fit in to this P458 structure that Augusti presented?
It could fit. It could fit. And for example, yes, I think it can be applied in general to hybrid HVDC, HVAC networks with any configuration. If you go to very large power systems, then the computation time increases, but yes, it could be applied.
Okay. And what is natural value of the computation time that you?
For a power system of 8 nodes,
yeah,
around 1 second.
1 second. Yeah.
Or,
okay.
Yeah, for the hybrid, the DC OPF is really fast.
Okay. 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 Thank you very much.